We are jumping straight into a deep dive today on a really critical paper. It's called DoPE, Denoising Rotary Position Embedding.
And this one is a really necessary fix for Ropey, which is, the cornerstone of positional encoding in pretty much every modern LLM. We're talking Llama, Qwen, Gemma, all of them.
Right. And we all know Ropey works well inside its training window. But the moment you try to push the context length, the performance just degrades, sometimes catastrophically.
And the big insight here is a total paradigm shift. People have been treating this as a frequency scaling problem.
Yeah, for years.
But the authors of DoPE, they redefine it. They say it's not a scaling issue, it's a noise problem. They look at the positional encoding as essentially a noisy feature map.
And that one small change in perspective leads to a pretty revolutionary solution.
Totally. DoPE is entirely training free. They use this metric called Truncated matrix entropy to find the specific attention heads that are causing all the noise.
The ones creating that dreaded attention sink.
Exactly. And then they just surgically suppress those noisy features right there during inference.
So the bottom line for you is that DoPE gives you robust extrapolation all the way up to 64K tokens. It stabilizes retrieval, it restores balanced attention, and you don't have to retrain or even fine-tune the model. A huge win.
Okay, so let's unpack that foundation, the Ropey extrapolation problem. As we said, it's the industry standard.
And it's elegant, right? It encodes the relative position, J minus I, using these rotation matrices directly into the dot product attention score.
Super elegant, but that elegance has a flaw, and it shows up the second you stretch the context. If you train on, say, 4K tokens and then try to run inference on 16K or 32K,
or even 64K,
the model just starts to forget what happened at the beginning of the sequence. It's really the Achilles heel for these long context models.
So the DoPE hypothesis is that this failure isn't random, it's structured noise.
Right. They're basically claiming that phenomena like the attention sink and, structural sparsity, they're all fundamentally caused by the low-frequency alignment of the positional encodings.
Low-frequency alignment. So if the rotation frequencies are too low, they just don't change enough over a really long context.
And that lack of change is the problem. It causes Ropey to induce what they call outlier channels in these low-frequency bands.
And you can actually see this.
Yeah, if you visualize the QK transpose attention matrix, they show up as these bright bands. It's just a few dimensions carrying an abnormally large amount of energy.
An enormous L2 norm. And those outlier channels are the source of the noise.
Precisely.
Okay, so this is where we have to get into the linear algebra a bit, but let's try to make it concrete. They connect this to the Gram matrix. It's essentially the covariance matrix for a specific Ropey frequency. How does that reveal the noise?
This is what's so fascinating. When those rotations stay inside a really tight low-frequency cone across the whole sequence, the projected keys and queries, they start adding together coherently. They start mixing properly.
It's almost like all the little signals that should be spread out just collapse onto a single highway. A traffic jam.
That is a perfect analogy. And that coherence, that traffic jam, forces the Gram matrix to get one huge dominant eigenvalue that scales linearly with the sequence length, n.
So it becomes a rank 1 matrix, basically.
Or approximately rank 1. And when your positional embedding collapses to rank 1, it means almost all the positional information is packed into one single direction.
And that one direction is what causes the bright bands.
And ultimately, the attention sink, because that single dominant component just gets louder and louder the longer the document gets.
So the failure is a kind of structural collapse, anisotropy. So we need a metric to measure that collapse, which brings us to their secret weapon, matrix entropy.
Right. If you look at the matrix entropy, HH, it tells you about the diversity of the spectrum. So a small HH means the Ropey bands have collapsed. You've got that spiky, low-rank structure.
And a large H?
A large H implies you have an isotropic covariance. It's a balanced encoding, like a perfectly round bubble where all the energy is distributed evenly.
But they didn't just use standard entropy. The real key here is the truncated matrix entropy. Why chop off the tail of the spectrum? What's the point of that?
The truncation is just super efficient and relevant. The truncated version, or it measures the effective dimensionality of only the dominant part of the spectrum. It just ignores the low-energy tails that don't really contribute much to the attention scores anyway.
I see. So for those problem child low-frequency bands, that R value just collapses down to basically 1.
Exactly. It confirms that near rank 1 structure. So the truncated entropy is like a really fine-grained anomaly detector. It's looking for that structural spikiness, not just general disorder.
And they found it was actually better.
Way better. Because the heads it selects, the ones that are good for extrapolation, they show this really clear periodicity in their similarity distribution. Full entropy doesn't capture that periodic structure nearly as well.
Okay, before we get into how they actually implement this, I have to ask the practical question. Calculating this truncated matrix entropy, isn't there an overhead cost? Does that kind of negate the benefit of being an inference-only method?
That's a great question, and yeah, they do address it. There is a calculation that has to happen, but it's a fixed overhead. You do it once at the beginning of the inference task for a given context length.
So it's not per token or per layer on every forward pass.
Exactly. And since they only select a subset of heads to actually denoise, the overall benefit from, not having your model's performance fall off a cliff usually outweighs that initial calculation cost. It's a one-time investment to buy you stability.
That makes a lot of sense. You pay a small price up front. Okay, let's look at the 3 ways they actually implement DoPE, starting with head selection.
Right, so it's very targeted. They select heads globally with a threshold applied to that truncated entropy. Heads with a smaller entropy are the spiky ones, the ones causing the problem, and they get flagged for an intervention.
First up, the surgical option, DoPE by parts.
Yeah, this one is really nuanced. For a noisy head they've selected, they apply a frequency band mask. And this mask, it only removes or attenuates the low entropy ROPE components.
So it's literally just masking out the frequencies below a certain threshold, the one corresponding to the training length.
Precisely. It's like frequency surgery. You keep the good isotropic parts and you cut out the parts that cause that rank 1 collapse.
Very clever. Okay, then you've got the simpler version, DoPE by all.
This is just a binary switch. If a head fails the entropy test, its entire ROPE positional encoding is just zeroed out, gone. If it passes, it keeps its original ROPE.
A quick and dirty way to just disable the problem.
Yeah, it just gets rid of the positional bias and relies on the learned attention patterns for that head.
And finally, the one that seemed to give the best results in retrieval tasks, DoPE by Gaussian.
This is probably the most interesting one conceptually. Instead of zeroing out the positional encoding for a noisy head, they replace it with isotropic Gaussian noise.
Wait, hold on. They fix a feature map that's too noisy by injecting more noise. That sounds completely counterintuitive.
It does, but it's not just any noise, it's isotropic noise. Remember, the whole problem was anisotropy that collapsed to a single dimension.
Right, the rank 1 problem.
So by injecting this statistically balanced Gaussian noise, they effectively kill that low rank mode and restore spectral diversity. It forces the head to look for the signal somewhere else because that dominant positional direction has just been completely randomized.
It's like a kind of stochastic regularization, but just at inference time.
Exactly. And the fact that it works so well kind of indirectly supports the theory that the layer-wise accumulation of these encodings might be well modeled by a Gaussian distribution anyway.
Let's get to the proof, the empirical evidence. They tested on Lamina 3.8b and Quen 2.5 Math 7b, pushing them way beyond their training windows.
Yeah, extrapolating from 8K or 32K all the way up to 64K. And they used dynamic NTK scaling as their baseline.
And the main test was needle in a haystack.
The gold standard for long context retrieval, yeah. But what makes their tests really rigorous is this split between original setups and noisy setups.
Tell us about that noisy setting. It sounds like they're deliberately trying to make the model fail.
They are, but in a smart way. In the noisy setup, they place attention sync symbols like the start of sequence token, which always attracts a ton of attention right next to the needle.
The piece of information the model is supposed to find.
Right. So it simulates a messy real-world document where some tokens are just naturally going to cause recency bias. And the baseline, dynamic NTK, its performance just falls off a cliff in that setup.
And that's where DoPE comes in.
Absolutely. The DoPE by Gaussian variant, it just showed remarkable stability. At a 24K context length, for example, the baseline scored about 75% accuracy in the noisy setting.
Okay.
DoPE by Gaussian jumped to over 84%. That 9-point jump is a massive recovery of robustness just from fixing the positional noise.
I also found the connection they made at extreme context lengths really fascinating. At 64K, which is just an incredibly sparse retrieval setting, the best strategy wasn't the most complex one.
That's right. When they pushed it all the way to 64K, they got the best performance by setting the truncation parameter for the entropy to R equals 1.
So if you set R1, you're essentially just selecting heads based on the spectral norm.
You are.
In plain English, you're just measuring how sharp the single biggest spike is.
Precisely. And this tells you something really critical about length generalization. The sparser the task, or the longer the context, the more concentrated and spiky that singular value distribution becomes. So at that extreme, the best fix is just to find and neutralize the one single maximally dominant positional direction.
So beyond retrieval, they also look at many-shot in-context learning, or MICL, on complex math reasoning. Here they found two major failure modes they called the curses.
Yes, the first one is the cursive length. Even with DoPE helping out, they confirmed that when you stretch the context length for reasoning tasks, the model's actual reasoning ability gets severely constrained.
So unlike retrieval, you can't just throw more examples at it and expect it to get smarter.
Right. The extrapolation limits are still very real constraints on the actual computation of reasoning.
And the second one, the cursive shortcut, is, well, it's genuinely alarming for anyone building complex prompts.
It really is. The cursive shortcut showed that if they put test examples into the context, kind of like a needle in the haystack, the overall reasoning performance actually dropped substantially, even on problems that had nothing to do with the example they inserted.
It suggests the model saw the new examples and just tried to pattern match.
Yeah, it tried to copy a template or apply some superficial shortcut instead of actually reasoning through the problem. And that led to a net decrease in its problem-solving ability.
Wow. It's like long context models, when you overload them, would rather cheat than think. That's a huge takeaway for you if you're designing complex ICL prompts.
Absolutely. It shows that positional stability is critical, but it doesn't solve the deeper problem of how these models use memory versus reasoning.
Okay, let's bring this full circle with the visualization. The entire premise of DoPE is that low entropy causes failure. How clear is that connection in their plots?
It's completely direct, unambiguous. The visualizations show that the heads flagged with low truncated matrix entropy are the exact same ones that produce that severe attention sink.
That tunnel vision where all the attention is just stuck on the last few tokens.
Right, ignoring the rest of the document. Meanwhile, the heads that survived the entropy check, the high entropy ones,
What do they do?
those are the functional heads. They correctly allocate attention to the needle, showing this balanced distributed pattern across the whole sequence. Low entropy means collapse and failure. High entropy means stability and success.
The power of this is pretty undeniable. DoPE gives us a simple, parameter-free, inference-only method that uses a really powerful spectral tool to fix ROPE extrapolation.
It really forces us to realize that length generalization isn't just about tweaking a frequency scaling factor, which is what dynamic NTK tries to do. It's fundamentally about maintaining spectral balance and structural integrity in that positional space.
Which brings us to the most provocative thought from this paper. They showed that for the sparsest setting, that 64K retrieval task, the best fix used in R equals 1 truncation.
Basically the spectral norm.
Meaning the optimal fix actually depends on the task's sparsity.
The level of intervention has to match the complexity of the context.
So the question for you to think about is this. Can we build truly dynamic LLMs that go beyond a fixed R threshold? Could we create models that measure this truncated matrix entropy layer by layer during inference and then dynamically adjust their effective rank or their positional encoding strategy in real time?
Optimizing that trade-off between retrieval and reasoning, based on the actual complexity of the input they're seeing at that moment.
That capability adaptive rank-aware inference, that would really unlock the next generation of efficient ultra-long context models.
It's a move from static design to a kind of dynamic cognitive control.
A fascinating future, all unlocked by just fixing the noise. Thanks for walking us through the elegance of DoPE.